So in the last lecture we have seen the definition of tradable derivative. So let me revise it once. Any derivative whose price satisfies the BSM differential equation is called as tradable derivative. What was the BSM differential equation? Daba f by daba t plus rs daba f by daba s plus half sigma square s square daba 2f by daba s square should be equal to rf. This is my BSM differential equation, right? So any derivative whose price f satisfies this differential equation would be called as tradable derivative, and any derivative whose price doesn't satisfy this equation would be non-tradable. Non-tradable in the sense it cannot be traded without creating an arbitrage opportunity. Okay, tradable derivative is the one which can be traded without creating any arbitrage opportunity. So this is a differential equation. So you must know that a given differential equation can have multiple solutions. Okay, so depending on the boundary conditions, so if you recall your differential equation theory, depending on the boundary conditions you can get multiple solutions. Okay, for example, for a European call option, we know that at time capital T, the worth of that option is maximum of s minus k comma 0. So let me write st minus k comma 0. This is for European call option, correct? So this becomes a boundary condition because at time capital T, this is the gain. This is the worth, right? So this becomes a boundary condition. So depending on what boundary conditions we are using, we get different prices which satisfy this equation. And hence, it's not that prices of a tradable derivative have to be from a very small set. Okay, this equation has many solutions. Okay, so let us try a couple of examples. So we have already derived optimal price of a forward contract, right? So let us try to check if this price satisfies the BSM differential equation. Okay, so what is the optimal price for a forward contract? We know that actually in a forward contract there is no price, right? But we decide something like a strike price, which is defined as S naught e raised to RT, right? This is how we had defined it. So at capital T, at time capital T means at the end of the expiry period, what is the worth? So it is ST minus K. Why? Because anyone who has a long position in a forward contract, long position means who has agreed to buy, will have to pay K rupees. So the payoff is minus K, and he or she will get an asset worth rupees ST. Okay, so ST is kind of a gain because that is the value of the asset that you are getting. Okay, so at in between time point, what would be the worth? Let me draw a picture. This is 0, this is capital T, somewhere here I have small t. So here if I want to evaluate worth of a forward contract, now at this time point my share price is ST, and a payoff of K here is equivalent to K e raised to minus R, because we have to discount for this much time gap. This much time gap means T minus T, correct? So payoff of K is equivalent to that, and the asset worth is equivalent to this. Okay, so at in between time point, FT becomes S small t minus K e raised to minus R T minus T, correct? So this becomes worth or price of a forward contract. Now we have to check whether this follows the BSM differential equation. Okay, so let us try. So what would be the LHS? For LHS we need to compute daba f by daba t. Daba f by daba t in this case would be first term will anyway vanish, so I'll be left with second term. So it would be minus r k e raised to minus r t minus t, correct? Because from here, from this power, I'll be getting minus r. Okay, sorry, I'll be getting plus r and then this minus sign, so overall it becomes minus r. Okay, then dabba f by dabba s would become 1 because I have s term here, and as a result dabba 2f by dabba s square becomes 0. Okay, so now let us substitute in the equation. So in the LHS of BSM differential equation, if I try to substitute this, I will get minus r k e raised to minus r t minus t plus r s. So I get r common and this would be s minus k e raised to minus r t minus t, and we know this is nothing but f at time t. Okay, so this becomes rf, which is my RHS. Okay, so we have proved that optimal price for a forward contract or a future contract, because they anyway have the same price, follows this Black-Scholes-Merton differential equation. It satisfies this differential equation. Okay, let us take a couple more examples. So for suppose we have some derivative, nothing has been specified except for the price, and the price is e raised to s, okay, or the payoff is e raised to s. Is this a tradable derivative? So again we have to do the same kind of checks. So dabba f by dabba t becomes 0 here, dabba f by dabba s becomes e raised to s, and dabba 2f by dabba s square also remains e raised to s. So if we substitute, we get LHS equal to rs e raised to s plus half sigma square s square e raised to s, and even if I take say e raised to s common, I'll be left with r, okay, s also I can take common, so r plus half sigma square s, which cannot be simplified further. Okay, so I can write e raised to s as f, so it becomes s f r plus half sigma square s. No further simplification is possible, so this is not equal to rf. Okay, so this is not a tradable derivative. Okay, this derivative cannot be traded in the market without creating arbitrage opportunity. Okay, let us take one more example. Okay, so let us take one more example. So suppose we have a derivative whose price is function of s and t both, and it is, of course, ideally any derivative price is a function of s and t both. So e raised to sigma square minus 2r into t minus t divided by s. So it's a pretty complicated equation. So we can try to compute again the same terms. Dabba f by dabba t. Dabba f by dabba t would turn out to be e raised to sigma square minus 2r into t minus t and then because we are differentiating with respect to t, coefficient of t would come here. So that is sigma square minus 2r, okay, and divided by s remains as it is because it is not going to get affected by the derivative. Dabba f by dabba s is simple because we have s only in the denominator, so I will have minus e raised to these things are constant, so sigma square minus 2r t minus t, and we have s square, right? And then dabba 2f by dabba s square. Here also we will have 2s as a derivative of s square in the numerator, minus sign will remain as it is, e raised to sigma square minus 2r t minus t upon, and now because I have s raised to minus 3, this becomes plus. Okay, so this s gets cancelled with this, and you can actually show that this, with these values, the BSM differential equation is satisfied. Hence, this is a price of a tradable derivative. Okay. So these were some examples of tradable and non-tradable derivative. I hope you got the concept. Now we have to move on to the next topic, that is risk neutral evaluation. Okay. So we have derived optimal price for a forward contract or a future contract. We have also derived optimal price in the binomial setup. Now in both these we actually made use of this, but now we have to go for pricing of more complicated derivatives, like for example option. So far we have never derived the actual price of an option. Okay, what we did was we gave some upper and lower bounds for the prices of options, but we never derived the price of an option. Okay. So for deriving price of any derivative, we have to make use of risk neutral evaluation. So what does risk neutral evaluation say? It basically says that expected rate of return on any investment should actually be equated to the risk-free rate of interest, because then only the things would be free from arbitrage opportunity. Okay, so expected rate of return would be same as risk neutral rate of interest, that is R. Okay, risk neutral rate of interest, which is R. This is the basic principle of risk neutral evaluation. We did this in a binomial tree model also. So for example, we know that expectation of ST is actually S naught e raised to mu t under its own probability measure. Okay. However, under risk neutral probability measure, this mu has to be replaced by the risk-free rate of interest. Okay. So under risk neutral probability measure, expected value of ST would become S naught e raised to R capital T. Okay. So how does this come into picture when we are trying to derive price of any derivative? So what we will do is, so price of any derivatives is calculated by first computing expected payoff from that derivative. Okay. So price of a derivative at time t, price of a derivative at time t becomes expected payoff from that derivative at time t. Okay, expected payoff from that derivative at time t. Now of course, when we are talking about derivatives like say European options, which cannot be exercised at in between time point, how does this work? So what we do is, okay, no payoff is going to happen here, so we compute payoff here, expected payoff here, and then we discount it back for this time lag. Okay, so that gives me expected value of payoff at this time point. So I compute the future payoff, expected future payoff, and discount it back for this at this till this time point. Okay, hence what we do is we compute expected payoff at time capital T. So expected payoff from the derivative at time capital T and discount it back. So e raised to minus R t minus t. That is how we derive price at any intermediate time point. Okay. So this is known as risk neutral evaluation. Now if you try to recall, this is exactly similar to what we did in the binomial pricing model also. In the binomial tree model, we did compute expected payoff and the probabilities. There were only two possible values in a single step binomial tree model, and the probabilities for computing the expected payoff came from the risk neutral evaluation. We didn't use the real world probabilities. At that time I had tried to emphasize that real world measure and risk neutral measure are different. Real world probabilities may be anything. Risk neutral probabilities were computed by making the portfolio riskless. Okay, so we derived the value of P, and then that P was taken as the the probability of going up, and then 1 minus P became probability of going down. Okay, so this is how we computed expected payoff, and we also discounted it back. Okay, so this is exactly similar to what we did in the binomial tree model. The only difference is now we are going to deal with more complicated setup. In the binomial tree model, it became a discrete distribution with just two possible values in a single step tree. In a two-step tree also there were only three possible values. However, now we know that okay, underlying stock price process follows Black-Scholes model. So it follows the geometric Brownian motion. It means that the normal distribution is coming into picture and not any discrete distribution with finitely many values. So when normal distribution comes into picture, for deciding price of an option, we will need to deal with the expectations of some functions of normal random variable. Okay, and then things become complicated because you can't have simple summation. You will have to deal with integration, that too because it is normal integration over an infinite range, and so on. Okay, of course the things are not going to be very tricky. They are just going to be slightly lengthy and maybe tedious, but they are not going to be tricky. They are really straightforward. Okay, so in the next lecture we are going to use this principle of risk neutral evaluation to get optimal price for a European call option. Okay, which has been pending since long. Let me stop here. Thank you.